Hello and welcome everybody to Introduction to Deep Learning. Today we're going to start with lecture 9 and we will talk about convolutional neural networks. So in the previous lectures, what we have been doing, we had often this kind of diagram for a neural network. And the idea of the network structure here was we had an input layer, we had a couple of hidden layers, we had an output layer, and then we had a loss function at the end of the day. And the way we structured our network was we had the width of the network, which was the number of neurons per layer. We had the depth, which was the number of layers. And then we had, all of these edges. They were the weights that were connecting the neurons between different layers. And everything we have been looking at so far was kind of like this structure, meaning we had this concatenation of layers, and we had always every neuron was connected to every other neuron in the previous and in the next layer respectively. And this is a fully connected neural network, meaning by fully connected, meaning that every neuron is connected to every other neuron. Also, we refer to it as an MLP, like as a multi-layer perceptron. And the idea here was that the architecture we could design was we could vary it in terms of width, depth, and this was deciding our capacity of our neural network. Now, this is everything what we have been doing right now, and today we wanted to bring a little bit of structure into that. So if we are using fully connected layers, and the abbreviation here, whenever it says FC, means it's fully connected. If we're using fully connected layers, then we can do this on images. So if we're doing this on images, we're gonna end up with something like this. So let's say we have an RGB image with RGB channels. So we have a 5x5 image here. It has 3 channels. This is the depth in a sense because it has RGB colors, so 1 channel per color. And if we're running a neural network layer with 3 neurons, we would have, if we say, we just take one axis here, right? We would have 5 weights if we just go one dimension. But of course, we are doing this for the entirety of the image. So in fact, we're having 25 weights to just take one slice of this image here. So we have 25 weights for the whole 5x5 image, but we're using only 1 channel, right? So every pixel here is connected with this neuron, meaning we have in total 5x5 weights. And now, since we have 3 channels here, we in fact have times 3 the number of weights. So in total, if we're having a 5x5 image with 3 channels, we're going to have in total 75 weights that we are using here, right? And this is just per neuron, right? So in fact, we have actually 3 neurons here. So we have 75 weights for each neuron individually. And this is kind of the problem with the fully connected layers. What we will very quickly see is that this doesn't scale very well. Or in other words, if I'm using a normal image, right? Let's say I'm going to use an image of 1,000 times 1,000, like a megapixel, right? It's not that much. And I have not just 3 neurons, but in fact, I would have something like, let's say 1,000 neurons to do anything meaningful. I would suddenly end up with 3 billion weights. And you can quickly guess that this is in fact highly, highly impractical, right? So we need to have something better to basically process images. And this is where we need to have a bit of structure. So the problem is basically we cannot make these networks arbitrarily complex. We can't just go deeper because the fully connected layers are pretty much just brute force. And so we have to make this practical somehow. So what do we want to do actually? Like, how do we make it practical? And this is very important here. We want to exploit the fact that we know we are processing images. So for images, we know a little bit more. And we'll get into this in a second, what we know here. So the better way than a fully connected layer here is we want to restrict the degrees of freedom, and we want to And the way we want to do that is we want to just have more structure in layers instead of having a brute force connectivity. And The very high-level idea of convolutional networks, which is what we're going to introduce in a second, is we want to do a concept of weight sharing. So we want to use the same kind of weights for different parts of an image. Or in other words, we want to exploit the knowledge that we are in an image domain. And what I mean by that is, we basically want to make sure that for an image, we first obtain a feature abstraction by applying local operators in a certain region, and then we're aggregating these features locally. And the argument is that the feature extractors for certain locations, they're always going to be the same feature extractors, right? They give you different features based on the input. But for instance, I'm going to make a very simple example. If I want to figure out a corner detector, and I want to detect a corner, like the way you detect a corner is the same no matter where you apply it. So you always apply the same filter, and this is what the convolutional network will be. You're going to apply the same filter everywhere. So what we're doing right now is we're basically saying, well, instead of like having this brute force connectivity, we're saying like, let's share the structure to obtain the features irrespective of the location where you're at. And that's the core idea of convolutional networks, right? So this way we have very, very powerful structure that we're introducing into the network architecture that allows us to save a couple of parameters, and then you can actually scale networks to make them deeper and get more powerful feature extractions. So convolutional networks, short, if you always hear CNNs, CNN stands for convolutional networks. That's an abbreviation that everybody uses. Some people just call it ConvNets, same idea. All the same word and means the same thing. And CNNs are pretty much the method of choice in computer vision methods. So whenever you're processing images in any kind of task you could imagine, for the most part, you're using convolutional networks. There are a few newer architectures that people started using, but that's something we're going to debate later. So first we have to understand how ConvNets works, because ConvNets made a big breakthrough in terms of absolute performance. And to give you a couple of example applications in computer vision, these are applications we will deal with, like classification. That's something we already know, right? Like, so give me an image, tell me a class as output. Localization, so you detect where's the object actually in the image. Object detection, where you have one image with multiple objects and you detect and classify the bounding boxes. Or are you doing things like instance segmentation, where for every pixel you would like to know the label and which object it belongs to. And for all of these computer vision tasks, they're going to have slightly different architectures, but there's going to be a concept later we're going to talk about, which is called the backbone. And for a backbone, the concept is always very similar. You're going to have a very powerful convnet, and this convnet gives you a bunch of feature extractions, and then you're doing these like specialized layers for instance, detection or so. You're doing it on top of it to extract the respective features. Okay, so as you could imagine, convnets, pretty important, very widely used. Let's jump right into it. So let's start maybe with what are convolutions. And I'm sure everybody has heard about it. And here it's actually nothing different what we're doing. What we are basically saying is we're having a function, right? We're having our function f here. And now what we do is we're having a filter kernel, and we are convolving the function with the respective filter kernel together, right? So this is a convolution of two box functions, which is this red box, that's our original function. And this here, the blue box here, is our convolutional kernel. And then what the convolution is doing is just basically getting the overlap between those two functions when you're sliding over it. And this is this green curve what you're getting here. It's basically measuring the overlap. That's what a convolution is doing, right? Typically, we're calling this an application of a filter kernel. The smaller function, or the smaller one, is typically called the kernel, and the larger one is the function itself. But in principle, it could be interchanged, right? This is just a way people started using it at some point. So, right? So f here is our original function, g is our kernel, and green is our output convolution. Now we can do the same thing with the Gaussian. We have here the red function here, we have the blue kernel, and we're convolving the two together, right? So Obviously, convolutions are being used in a wide range of areas. Traditionally speaking, this comes mostly from signal processing, where people using convolutions actually in an analog sense. If you're talking about convolutions in the context of neural networks, we are mostly going to talk about convolutions in a discrete case. What does it mean in a discrete case? Well, the discrete case makes it even a lot simpler. So all you have to do right now is you have to discretize your function into, let's say, a vector of values. You do the same thing for your kernel. So you discretize your kernel into a bunch of values. And now you are going and taking the kernel and sliding the kernel over your function and computing a single value for each location where you are sliding the kernel on top of the function, right? So what this means here is if I have the function f here, this is, let's say, it's just a 1D array, and I have a 1D filter kernel here, so I have a three-dimensional filter, and I have this function here. Now what I do is, if I want to convolve these two, I'm just going to go ahead and apply this filter kernel here, and just take a dot product between those two respectively. That's the discrete case of a box filter. It's very, very straightforward. That's the easiest thing. So just compute basically the average here, right? So I have 4 times 1/3, 3 times 1/3, 2 times 1/3. And if I'm adding it up together, I'm going to get 3 here as an answer. So what I do when I use the convolution is I'm computing one value for every location where I'm sliding the filter over here, right? For this starting location, I'm gonna get 1, 3 here. And now what I do is I slide the filter 1 to the right. So I'll slide it here. So now I have 3 times 1/3 plus 2 times 1/3 plus minus 5 times 1/3. And if I'm adding this all up again, I'm gonna get 0 as an answer. So the result of this convolution at this location is going to be 0. And now I continue. I just slide it once more over. I have here 2 times 1/3 plus minus 5 times 1/3 plus 3 times 1/3. And if I add this up again, I'm going to get 0. And I'm continuing. Minus 5 times 1/3 plus 3 times 1/3 plus 5 times 1/3 is 1. 3 times 1/3 plus 5 times 1/3 plus 2 times 1/3 is 10/3. 5 times 1/3 plus 2 times 1/3 plus 5 times 1/3 is 4, and so on, right? So I'm going to continue this for every single location where I can apply this filter to. Obviously, I'm sure many people have seen that. I'm just going to go over it to make the concept very clear that we are here in a discrete convolutional case. And in this case, what this example was showing is actually a 1D example. Now, of course, I cheated a little bit, right? I don't have values here and I don't have values here. The reason is I don't know like what value I should use here, right? I just don't know yet. And so the boundaries is kind of a bit of an ill-defined issue for the time being. So I just left it out, right? So I can't compute a value at this point in time. And the simplest option, what we can do to deal with these boundary cases is, well, we just don't have a value here, right? And then we just don't have a value here either. So in this case, we would just say, well, we just shrink the output dimensionality a little bit, right? And in this case, we are going and making this whole array one smaller on both sides. Okay, so that's one option. That's often being used also in the concept of convolutional networks. Sometimes it's even desired, and sometimes the architectures are designed around like how you changing these respective things. Okay, what's the other option? Well, the other option is you do padding. Zero padding is the most common version probably. So what you're going to do is you're just expanding your original array here, or your original input tensor by 1 here, because my filter is a 3x3. Sorry, my filter is a 3-dimensional filter. We're still in 1D here, right? So I have a 0 here, I have a 0 here, and then I can actually apply this kernel here and apply it here, because then I have 0 times 1/3 plus 4 times 1/3 plus 3 times 1/3, and this is 7/3, right? And I can do the same thing here on the other side accordingly. So in this case, if I, for instance, don't want to change the dimensionality of the input versus the output, of this current filter operation, then I have to use some form of padding. And zero padding is just the most common version ever. All right, so this was pretty straightforward. This was the one-dimensional case. Now what we're going to do is we're just going to do this on an image. So now we have a two-dimensional case, and we're going to start with a 5x5 image and a 3x3 kernel. Of course, it's not a realistic setting because typically our images would be larger, but we wanted to make sure we fit this somehow to a slide here, so we're using a relatively small image. In this case, we're using a 5x5 image. Right? So we have values here in this 5x5 image. We have a 3x3 kernel. We have values in here. So what do? Well, we just do the same thing what we had been doing before. We take a dot product between all of these values and this value. So in this case, we have -5, something is wrong here. I'm not sure where this value comes from. I don't see a 5 here. Ah, got it. Now I got it, how it starts. It starts in the middle, actually. Here we're starting with 5 times 3. Then we have -1 times this 3. Then we have -1 times 2, -1 times 0. Then we have 4 times -1, and we have zeros everywhere else. Okay, so I was a little bit confused because when all it's doing, it's -5 times 0 plus 3 times -1 plus 2 times 0 plus -1 times 4 plus 3 times 5 plus 2 times -1 plus 1 times 0 plus 0 times -1 plus 3 times 0. Just a different ordering. Maybe I should have done this a bit better on the slides. Okay, but if you're doing this, take the dot product between this and this. You're going to get 6 here as an answer, and this is your output for this filter location, right? So we've just done the filter for this 3x3 location. And now what we're doing is we are moving the location 1 to the right here. And in this case, we have the same thing again, right? Again, to do it in the order here, it's 5 times 2 minus 1 times 1 here, 3 times -1, -1 times 3, and 2 times -1, that's this one here, right? So same thing here, we're just saying we're doing this one times that one, we're doing this dot product, and if we're adding it all up together, we're gonna get a 1 here. Okay, now we're doing again here, same thing, 5 times 1, -1 times -5, -1 times -3, -1 times 3, -1 times 2. We're adding it all up is equal to 8, right? So conceptually, right, I mean, all that's a bit confusing here is the ordering, but it's very straightforward, right? So we start with the filter here, take a dot product, take the filter here, take the dot product, take a filter here, take the dot product, right? And for every filter location, we're going to compute one respective output value. So we have moved the filter once, twice, 3 times. So we're going to get 3 different output values. And now we're shifting the filter 1 to the bottom here. So we now have this one here, right? So here we have now this times that. This is the computation here. This one gives us -7. We're moving it 1 to the right here. This one gives us 9. We're moving it 1 again to the right. This one gives us 2. This one gives us -5. This one gives us -9, and this one gives us 3, respectively, right? And what you can already see here is, well, it's a 5x5 image. We apply a 3x3 kernel. We have chosen kind of this option 1 of just reducing the size because we have now padding. So out of a 5x5 image with a 3x3 kernel, we're going to get a 3x3 output because we have 3x3 valid filter location where we can apply it. Okay. Now in computer vision, actually, filters is also not necessarily a new thing. In fact, filters have been used for all kinds of different stuff. So for instance, if I take an image and want to do edge detection, this is a very common edge detection filter. or this is a box mean filter, right? It's just blurring the image. This is a sharpening filter, which is kind of using the gradients. This one is using a Gaussian blur filter, similar to that one, except with a different blur kernel. And the core idea in computer vision is that these filters were kind of handcrafted for the most part. And that's actually something that people use to learn to extract features like sift, surf, and these kind of things. They're basically filter based in one way or another one. And they're applying these filters kernels in order to get some features extracted. Now, the core concept of quote-unquote modern deep learning is now we don't want to handcraft these filters anymore. In fact, we want to go ahead and learn these filters, right? So now, instead of having these predefined filter kernels that somebody like crafted to have a desirable feature extractor that we care about, we would like to go ahead and learn these filter kernels. And the unknowns, the weights of our neural network, are then the respective filter kernels that we are optimizing for. So in other words, we're trying to find good filter kernels that give us good feature extractors that we can then use for our respective downstream tasks, such as classification, detection, and so on. Okay, so how does it work with RGB images? That's something we haven't talked about yet. So if we are talking about an RGB image and a bit of a more realistic dimensionality, we're gonna get up something like this. So our input image here is 32 squared, so it has 32 times 32 resolution. It has an RGB channel, so it has a depth of 3. And depth always means, like, think about this as a three-dimensional thing. You have a width of an image, a height of an image, and a depth of an image. So here we have 32 times 32 times 3. That's our input image. Like, we're just going to visualize it this way for now. And for the most part, we're going to have a depth of 3 in the input, right? Because we're using RGB images. And now what we are doing actually is our filter is becoming also kind of like three-dimensional, right? So our filter right now has to make sure that we're not only convolving over the XY location, over the width and the height, but also over the depth respectively. And that's what we're doing here right now. Now our filter kernel is, it's a 5x5 filter, but it has to match the depth of the input. You have to take all the depth here into account. So our filter is 5x5 times 3. This 3 here must match the depth of the input. Otherwise, we can't apply the filter. The filter must extend to the full depth of the input, right? Okay, and then we do the same thing what we had been doing before. We are convolving the filter with the image, so we're sliding it over and apply a filter operation at each location. And applying the filter location means we simply have a dot product between the current location and the respective filter kernel. And in this case, applying the filter means we have 5 times 5 times 3 operations here to do. It's a 5 times 5 times 3-dimensional dot product that we have to apply. Okay? And if we're running this, let's make it a little bit more mathematical. We have the input. This is the number of pixels here as input. We have our conv weights, which is our W. This is similar to what we had before, right? And we're computing one number at one time. Right, so we have this ZI location here. And this is equal to dot product between the filter weights W and the xith chunk of the image. So xi means this crop here of the image. And here, as I said, we have 5 times 5 times 3 dimensional dot product that we have to apply. And similar to the MLPs, what we had before, we don't just apply the filter, but we also have a bias here. So we have the filter, it's the dot product between the filter weights and the image chunk, plus a bias that we end. And now you can see how many weights we have here. Well, we have the weights of the filter, that's our W, and we have our bias, which is 1 per filter kernel, right? So if I have a 5x5x3 filter kernel, that means I will have in total 76 weights, right? I have 75 for the filter kernel itself, plus 1 bias, right? That's what we have to do. Okay, so let's continue. Let's say we're having this input image here. We're applying this filter at every possible location where we can apply it, no padding. Then we are going to get, like, in total 28 28 times 28 valid location where we can apply this filter to. And this is, we're sliding simply this conv kernel over all the spatial locations where it's possible and computing the respective output ZI. And as an output, what you're getting right now is you're getting something what's called an activation map. Later, this will become a feature map. It's not quite a feature map yet. It's a bit low dimensional, but we'll make it high dimensional later. But in this activation map, we know that this has to be 28 times 28 dimensional. Why? Well, we're having a 5 by 5 filter kernel and a 32 times 32 input image. So at every end, we are losing 2 locations where we can apply the filter to, right? So like in total, we are reducing the dimensionality by 4 for each axis, right? So the 32 will become 28 because that's how many valid filter locations we can apply. And as an output here, we're going to get a 28 times 28 dimensional activation map. Now, you see here in red, there's a 1 here. You might ask, well, why is there a 1 here? Well, like at this point, when you're applying the filter, there's no concept of depth anymore. The concept of depth just comes into play how high dimensional the dot product is. Now, how can we basically get a higher dimensional output here again in terms of the depth? Well, the idea is we will now have not just one filter per layer, but we will have multiple filter kernels per layer. And this brings us to a convolutional layer, right? So now the idea is what we had right now, we had one filter kernel. We applied it at every possible location here in the image. And now what we do is we're just applying a different filter kernel with different weights for the same spatial locations. And I'm going to make this very simple right now. I'm just going to have 2 different filter kernels that I want to apply with 2 sets of weights and the respective bias, right? And if I do that, I'm going to get an activation map. I'm going to get 2 activation maps. Right? I have 28 times 28 for the green one, and I have 28 times 28 for the blue one. Right? And now my output in total is 28 times 28 times 2, because I have a 2-dimensional depth in the respective output map, right? Okay, and the idea here is that we're not just going to use 2. In fact, we're going to use many more. So if I use 5 filters, each with different weights, I'm going to get as output a 5 times 28 times 28 dimensional feature map as output. And that's what the conv layer is about right now, right? So this is actually all what we're doing at this point. We're now saying is we're having an input image with a certain dimensionality, 32 times 32 times 3. And now we're applying a set of conv kernels. The number of these kernels depends the feature dimensionality in the output, and the XY location depends on the filter kernel size and how many valid locations I could have applied the filter to, right? And then I continue, right? This is one conv layer right now. Okay, so if we're summarizing this very quickly, a convolutional layer is defined by the filter width, the filter height. The depth is given by the input, right? You don't have to define that. Like whatever depth the input has, like RGB image has 3 depth channels, so you gotta use a filter of 3. So it's the number of weights per filter are width times height times depth plus 1 for the bias. That's like the number of weights I have per filter. And then the number of different filters, meaning how many different unique weight sets I'm gonna use, that depends the output dimensionality in the depth. This is like how many channels I have in the output, right? And the whole level idea now is we are gonna backpropagate through the whole thing what we just described. So now we want to optimize for all of these filter weights. And the hope is that each of these filters that extracts a certain characteristics of the image, right? Like one, you could imagine it as a set of like, well, edges, corner points, right? But it's not hard-coded anymore. The network learns how these filter kernels have to look like in order to get the respective outputs. Okay. In practice, these filters look something like this. You can actually visualize those ones. So each filter now captures different characteristics. So I was trying to say, oh, we have horizontal edges, vertical edges, circles, and squares. But in practice, you're going to get something that looks like this. And there's a way you can visualize these features. There's like the Seiler and Fergus paper with the ECCV paper in 2014. And these are very low-level features. Like, again, kind of like edges, but just a little bit different. So these are the filter weights that we're visualizing here. And you can already see what's very practical. You see how many filter weights we have. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, right? So I have 5 times 6 filter kernels, actually, right? And each of these kernels, they have a different set of weights. They don't share any weights. The weight sharing kind of only happens for one filter kernel across the locations where you apply it. And the most important thing when you're thinking about convolutional networks is to always get through the dimensionality of all of these things, right? And what I mean by dimensionality? Well, dimensionality for the most part is defined by 3 things, which is the input, the filter, and the output. So if I have an input image of 7 by 7 pixels, I have a 3 by 3 filter kernel, and I have an output then of 5 by 5. Why do I have that? Well, I have 5 by 5 different filter locations where I can apply my 3 by 3 filter in a 7 by 7 input image, right? So you can see it here, 1, 2, 3, 4, 5. This is in X direction, and in Y direction it's the same thing, right? So you can go 1, 2, 3, 4, 5, and you could do the same thing in the Y direction here as well. Now, you can change these dimensions and cheat a little bit. Or like not cheating is maybe the wrong term, but you can modify this slightly and you can say, well, I don't want to apply the filters at every location. I might want to skip adjacent pixels. And that's a concept of what's called using a stride. So what we have seen before was always using a stride of 1, meaning that for every possible location, we wanted to go ahead and apply the filter kernel, right? This was a stride of 1. Now, there's a concept, you can just have a different stride. So stride just means how many filter locations do I want to skip. So if I use a stride of 2, I'm not going to take the next kernel, which would be here, sorry, the next kernel location, which would be here. I'm going to skip 2, right? I'm going to from here to here, and then I'm skipping 1 again, and I go to here. So if I use an input image of 7 by 7, I have a 3 by 3 filter and a stride of 2, that would mean that my output is going to be 3 by 3, right? Instead of 5 by 5, what I had before, right? Remember here, this was stride of 1, had 5 by 5. And now what we're doing is, like, see the difference, right? So the stride determines how many locations I have, basically. Okay. Now the question is, what if I have a stride of 3 here? Well, if I have a stride of 3, I have one location here. I skip 3, so I will here. And I skip 3 again. Now, this is a little bit of a problem. So this doesn't fit, right? So now I have kind of like only 2 valid locations, and I have kind of this half location left. And this is actually something that is illegal. So the stride can only be, it's illegal to have basically fractional reminders, right? And this is a big problem. If there's a fraction, then we're gonna have an issue. And that's something that is illegal in all the deep learning frameworks. So if you're running this in PyTorch, it'll most give you a compiler error right at the beginning. Okay, but we can actually apply some formulas here. It's actually very straightforward, right? So the output dimension is very obvious. The output dimension is we have the input minus the filter size divided by the stride. Input dimensionality minus filter dimensionality divided by the stride plus 1. That's what we care about, right? And we have this in both dimensions, of course, right? So this is the filter width, filter height. This is this f here. Input is n. So if I have an image of 7 by 7, I have a filter of 3, and I have a stride of 1. It's 7 minus 3 times 1 plus 1, which is 5, right? So 7 minus 3 is 4, plus 1 is 5. If I have a filter of a stride of 2, it's 7 minus 3 divided by 2, plus 1 is 3. And now here we have this fraction, right? We have 7 times 7 input image. We have a 3 by 3 filter, and a stride of 3 is illegal because it would be a 2.3 dimensional output then at the end of the day. So we can't have that. We have to have, everything has to be discrete. Like, this is the nice part about convolutions. Whenever you notice that this is this is happening to your architecture, you have a bug and you have to fix it, right? Okay, so let's look at this, how this looks in a full network. So in a full network, we can also look at the dimension. So what we're doing right now is we are going ahead and having an input image. We have an input image of 32 times 32. That's kind of the dimensionality what we're using right now. We're having a 3-channel input. So it's the RGB values. It's 32 times 32. And what we're doing is we are applying a ConvNet layer here with 5 times 5 dimensional filters times 3 because of this 3 here, right? That's given. So each filter here has in total 5 by 5 by 3 plus 1 weights. We are applying 5 filters. So we have 5 unique weights of here. So you can already see how many weights we have here, right? So it's 75 plus 1 is 76 per filter. So it's 76 times 5 filter weights in total that we have here. If you're applying this, we have no padding at the moment. Then we're shrinking it down here from 32 to 28, right? With this formula with this one what we had here. So n minus f divided by s plus 1, right? Then we go from 32 to 28. Then here we just made these numbers arbitrarily up, right? So now here we have 5 times 5 dimensional filters again. It has to have 5 channels because we had here 5 channels as well, right? So this is already 5 times 5 times 5 different weights, all right? That's already 125 per filter, plus the bias, plus another one. And in this case, we decided we're using 8 filter banks. So the output dimensionality will have 8 dimensions because of these 8 here. And since we're using a 5-dimensional filter here, we're going to shrink from 28 to 24. Okay? Well, then we have another layer. In this case, we're using 12 filters of 5 by 5 again. This 8 here has to be 8 because of here. And remember, here we're having 5 times 5 times 8 plus 1 filters already, right? Okay, so this is the 12 filters that we have. And the output then will go to 12 dimensions because we have 12 filters. And it's going to be 20 times 20 because it's still this 5-dimensional filter that reduces the dimensionality by 2 in each direction, from each side basically, right? Okay, so this is how it works, like roughly from a dimensional standpoint. Like, I hope that you understand the dimensionality. If you don't do it, the good thing is this is a YouTube video. You can just go back, replay it again, and make sure you really understand how the dimensionality here connects together. And a good exercise is always to imagine per layer, per filter, how many weights do I have respectively. Okay, now here's a couple of considerations right now. So this is kind of a ConvNet architecture, but shrinking it so quickly is, not always the best idea. Sometimes it is, depending on what kind of backbone you want to use. But sometimes it's always not such a good idea. How can we prevent it? Well, one way to prevent it is to use padding. We've talked about this already. Well, sizes get too small too quickly. There's another issue, right? The corner pixels are only going to be used for one filter kernel, right? This would be also a problem, right? If I just wanted to use this pixel that I would have a 3x3 kernel, I would only use it a single time for this layer. This would also be a problem. So you want to balance this a little bit out and want to make sure that boundaries are treated, more equally and not being put to the edge. So what do you do? Well, we're going to use padding. 0 padding is the number one thing that people use. So in this case, we have a 7 by 7 input image. We have a 3 by 3 kernel. So we need a padding of 1 to compensate for that. So now we have a 0 padding of 1 in each axis, and then we don't lose any size. Now we have to adapt our formula for the output sizes though, right? So what do we have right now? We have here an input image of 7 times 7. We have a 3 by 3 filter. We have a padding of 1, and we have a stride of 1. That means the output is going to be 7 by 7. So we didn't change the input and the input dimensionality. The output size is now computed by input dimension plus 2 times the padding, because it's going in both directions, right? Basically, in other words, the padding just makes the input image larger. You could imagine it this way. minus the filter kernel divided by the stride plus 1, and in both directions, right? And this one here denotes the floor operator, so you're rounding down. As in practice, an integer division is performed here, right? So you have to compensate for that as well. Okay, so that's what we're doing here right now. So the padding allows you to maintain the current dimensionality of your data at this point, right? So of your input images, you don't necessarily want to change the dimensionality. And yeah, the padding allows you to keep it. Okay, so in this case, we keep the 7 by 7. Right. Okay, so there's types of convolutions. Well, we have valid convolutions that use no padding. We have same convolutions where the input and the output size doesn't change. And then this is basically the same thing. It's a valid convolution to use that. Using no padding, then the size changes. Or you're using the same convolution and you want to make sure that output and input stays the same. Then the padding is always set to filter minus 1/2, which makes sense because that's what the overhead is basically, right? So f is the kernel size here. So if we're setting the padding to this, f minus 1 divided by 2, then the input and the output size will remain the same, and we don't change. We don't change it. So these are the two types that we're basically doing. One of them is we don't use any padding, or we're using something like this where we keeping and maintaining the current resolution. Okay. Let's have a look at a few more numbers with another example. And this is really critical that you understand the dimensionality here, right? If we're having an example again of an input image of 32 times 32, 3 channels for RGB, we have 10 filters, 5 by 5, stride of 1, padding of 2. Depth of 3 is implicitly given because of this 3 here. I typically like writing it down just to make sure that, there's actually a factor of 3 in here. So sometimes you don't provide it, but you need to understand you need these weights, right? It's like this 3 means you need 3 times as many weights per filter kernel. Okay, so this is our example. And if we're just doing that, we have an output size of 32 plus 2 times 2 minus 5 divided by 1. It's a stride. Plus 1, and this is 32. And in this case, we are maintaining the dimensionality. Again, remember this formula here. It's input dimensionally plus 2 times padding minus filter size divided by the stride plus 1. Okay? And here's like this coloring, which makes it clear, right? We have 10 filters that determines the output dimensionality. We have an input image of 32 that determines this 32 here in the output size. We have the filter of 5, which determines this part of the formula in the output size. We have a stride of 1, which is that makes the division by 1. And we have a padding of 2, which is this plus 2 times 2, right? Okay. This is basically what we're doing right now. This is our dimensionality. And we can have another example here. So this is another example here where it's the same example, but here we're looking at the number of weights, right? So we're looking at the same example here. The number of weights is 5 times 5 times 10 without the bias, but it's 5 times 5 times 3, which is this one, plus 1 for the bias is 76, right? So if I have a 5 by 5 filter kernel, 3 input channels means 5 by 5 by 3, which is 75, plus 1 for the bias. So I have a filter kernel of 76. Since I have 10 filters in total, I in total have 760 parameters in this layer, right? And you can compare it to a fully connected layer, depending on how many neurons you had, right? So that would already be a lot larger. This would be, if I have a fully connected layer, I have per neuron, I would have 32 times 32, right? That's 1024 times 3, that's about 3K per neuron, right? You see that this is like vastly fewer number of parameters than an MLP would have in comparison, right? Okay, let's have another example. And this is something that you should probably know how to answer by now. You're given a convolutional layer with 4 filters, kernel size of 5, stride of 1, and no padding that operates on an RGB image. This is kind of the trick thing. Operates on an RGB image means we have 3 channels in the input. And now is the question, what are the dimensions of and the shape of its weight tensor? Well, what is the weight tensor? The weight tensor is our filter kernel. Well, what do we care about? Well, we do care about a few things here. We have a 5x5 kernel. The stride doesn't matter. Like, it doesn't matter how many times I apply the filter kernel. That's completely irrelevant for the number of weights. I have 5x5 for the spatial dimension in x and y. I have operating on an RGB image, so my depth here is 3. So it's 5 by 5 by 3. So 75 plus 1 for the bias times 4 because I have 4 of the filters, right? So if I'm looking here, I have 3 input channels, I have 4 filters, and I have a 5x5 filter kernel. So this is going to be what my tensor is going to look like. What's not in this answer here is obviously the bias, but you get the idea behind it, right? So my tensor of my weights is going to be 3 times 4 times 5 times 5. Right? Now we have all concepts in order to build a neural network. And that's what we're going to do. Now we're building our CNN. Well, we have already seen this prototype. Now we simply concatenate these conv layers together. This one little detail, what I have not mentioned yet, but this is very critical, you actually, after every layer, you still need the nonlinearity. Right? Every time you're applying a filter kernel, you're feeding the output of this dot product where you applied the filter kernel into nonlinearity. And this is the same design choices for nonlinearities that we have seen before. Like, people have tried all kinds of them. Modern neural networks, for the most part, use ReLU. That's why our CNN prototype will look like this here as well, right? So we have conv, ReLU, conv, ReLU, conv, ReLU. And the dimensionality of each of these conv layers is going to be slightly changing depending on, well, okay, the filter sizes, in this case, the 5x5 is always the same, but the depth changes depending on how many channels I had before. And that depends again on how many filters I have applied in the respective previous layer, right? So this is our CNN prototype. And the convnet is now the concatenation of these conv layers and these activations. Okay. Well, if I'm applying this on a very abstract level, you're going to get something like this. We've already seen these ones. These are kind of like early low-level feature extractions. Again, this is visualizing the weights of the kernels when you're learning this. Sorry, I should go a step back. So what we're learning here is basically training a neural network on a large image data set and then examining how the weights look like in our convnet. These are the results after applying backpropagation, SGD, for many epochs on a large image data set for a classifier of images. And what this is doing here right now, it's visualizing the weights respectively. So for each layer, we can take the weights of the filter kernel and visualizing them like this. And this basically tells you, like, this visualization tells you on what kind of shapes is my filter going to be active. Like, think about it this way. You're sliding this over, it's like this convolution, and at some point the filter says, oh, look, I saw something, and then my output goes up, right? Like the edge detector, for instance, right? What we had before. Except, again, these are learned kernels. And they can be larger kernels too. And now what we do in an abstract sense is we can visualize them at different layers. So you're kind of getting low-level feature extractors. That's what these ones look like. You get mid-level feature extractors. You get a bit more concrete patterns already. And it turns out this is kind of interesting. So the deeper you go on your network, the more specific and the more concrete these structures are being, right? This is more low-level and this is already more high-level features. But this is kind of funny. And you can now go ahead in your convnet and examine at every layer how these features are shaped and how they look like respectively. Okay. Yeah, that is basically convnets. Now we know how to use convolutions. We know how to stack them together. So we know how to change sizes respectively with like strides and padding. We know we can apply different dimensionalities here. like basically how many filter kernels do we apply. We can stack them together. We have nonlinearities in between. We can use backpropagation to optimize the filter kernels, and then we can use them for certain downstream tasks. We'll get to this in a second, how we exactly use them for downstream tasks, but this is already giving you a hint of, okay, this is how the feature extraction is actually going to look like in work. Now, the next thing what I would like to do is, I would like to talk a bit more about ways in a ConvNet to change the dimensionality. Well, we've already seen a couple of things in the resolution. What we can do is we can go ahead and apply things like padding, strides, and stuff like that. But there's special layers that allow you to change the size of your images accordingly. And these operations, they're called pooling operations. So pooling operations is very straightforward. So the idea here is you're going to have an image, or a feature map in this case, that is 224 squared, and we have 64 feature channels here. That's just an output of a ConvNet after a certain layer. And now what we would want to do is we would want to go ahead and downsample this image, quote unquote, pool it to a smaller resolution of 112 squared, same number of feature channels. So pooling doesn't change the number of feature channels. Pooling just changes the width and the height of our resolution here, right? And we just want to do some downsampling. The question is, how can we do some downsampling here? We'll also see how we can do upsampling, but let's do downsampling first. So we go from 22 to 112 here. And the simplest thing how people do this in a neural network, specifically as part of ConvNets, is we're going to do something called max pooling. Well, what is max pooling? Well, in this case, we have kind of a 2x2 filter kernel, except that this kernel doesn't do any filtering. It just chooses the maximum value in this 2x2 area. So in this red area, we have a 2x2 chunk here of the image. We just pick the largest value. The largest value in this case is 6. So here we get a 6. Then we take this green area. It's a 2x2 area. Largest value is 9. So 9 is here. Then the blue area. So we have 3 here as a maximum. That's 3. And here we have 2 4s, which is then leading you to 4. So this was a very simple operation of downsampling, and we're just ditching all the values that are not the respective maxima. And you can think of this with arbitrary dimensions. You can go 3x3, 4x4, 5x5, and so on. And in this case, there's no learnable layers. We can basically just use the pooling layers to change the dimensionality. But you can also interpret it kind of as a higher level meaning. And a higher level meaning here would be, well, the conv layer is kind of like a feature extractor, right? It computes a feature in a certain region. Like, for instance, you have an edge detector, you get a high value when it's an edge. And the pooling layer is kind of a feature selector. So it picks the strongest activation in a region. Well, okay, in fairness, a max pooling layer is a feature selector, right? It picks the strongest feature in a certain region. And these two things, they go very well together. So in many architectures, you see combinations of that. You see like conv pool, conv pool, conv pool. That's a very common way of combining the two things. And first extract features, then change the resolution by selecting the feature in an area, and so on. This is very common, these pooling-based architectures. Okay, so dimensionality-wise, we can do the same math what we had been doing for the convolutions. Here we're having an input with the volume, so width times height times depth. Again, for an RGB image, this would be 3. This is our image resolution, or our feature map resolution. And now we have two hyperparameters here. We have the spatial filter extent. Like in this case, we saw 2x2, but you can do it for 3x3 as well, of course. So that's the size of our pooling. And we can also apply a stride. Same idea, right? We can say, oh, don't apply this filter everywhere, just apply it to certain areas. And in this case, we have seen a stride of 1, but you can also do pooling with a certain stride, right? Okay, then we have a filter count k and padding p from the filters, which here doesn't make any sense, right? Like if I have 5 times the same filter, it's still going to give you the same maximum, right? Because all of the maximum operators are going to be the same. Padding also makes not so much sense. If you do zero padding, well, it's certainly kind of pointless, because like you want to go with the values that actually exist. So if you're cropping some stuff off the image and you're applying the pooling layer only on parts of it, you can still do the same maximum operator. You don't need to pad anything here. Okay, and then the output dimensionality is defined by the following formula, right? You're just taking the input size minus the filter size divided by the stride plus 1. So resolution minus filter divided by stride plus 1, right? And the dimensionality here of the depth, that one you just keep the same here, right? That one you don't change. Yeah, and on a high level, what's very important, there's no parameters here, right? There's nothing to learn. It's just a fixed function you apply to quote unquote select the right feature in the region, applying your maximum operator. Okay, that's pooling. Few examples here, common settings, what people are using. There's typically filter size of 2 or filter size of 3 is common. Stride of 2 is also very common, right? So you skip basically the respective locations. Here, this was a stride of 2, right? Because we didn't apply, like we applied it here, we did not apply it here, and so on. So this is a stride of 2, and it's a 2 by 2 filter that we applied. That's the most common thing. Okay, yeah. So what I haven't thought of it yet, we can basically take different operators here. Instead of a max pooling, you can also take an average pooling. Average pooling, same idea, except that computing a maximum, you're simply computing the average of the numbers. So here we have the average of 3 plus 1 plus 6 divided by 4. That's 2.5. 3 plus 5 plus 7 plus 9 divided by 4 is 6. Right? And so on. And average pooling is also often used. It has a slightly different effect. It's not just a selector. It's kind of giving you the average feature response in a certain area, right? I should say probably for the most part people using max operators for the feature selection, but average pooling can also become very handy for certain types of architectures. Okay, sometimes they use, well, generally pooling is used for deeper architectures in the network. And yeah, well, in principle, you can also do min pooling, like a minimum pooling, but it's similar effect than max, right? Okay. All right. So that's pooling. I think that should be very straightforward. We can add pooling to our neural network prototype. I mentioned this already, that in larger or deeper architectures, people continue to stack these things together. So people, for instance, can have stuff like this. They have a conf layer, a relu, conf, relu, pool, conf, relu, pool, conf, relu, pool, right? This one, for the most part, means always it's going to be a max pool. By the way, minimum pooling combined with relu, you have to be a little bit careful, because relu in itself is a maximum with 0, right? So that might not have the desired effect that you want to get. Okay, but this is very common that you get these architectures. The last thing, what we haven't talked about it, how do we do things like classification right now, right? So we talked about feed an image in, have an architecture like this, and then get some output. But we still need to get our loss function, we need to get score functions and stuff like that. And at some point in your network, you have to basically have a fully connected layer. That's what this FC here is at the end. So typically the way this works is you're running a series of convolutions combined with pooling. You're typically going down in spatial dimension at some point. And then at the end of your network, you're running a fully connected layer that basically maps it to a classifier, right? So like you map it to class vectors from this two-dimensional shape of the feature map. And again, these feature maps at the end are typically very tiny. So the reason why you want to make them, well, tiny in a sense of like, they have a very small spatial resolution and they have a very high depth. So what's very common here is something like, I don't know, 32 times 32 times 64 or something like this, right? Or even smaller in terms of spatial size. And then you're running a fully connected layer at the very end of the day that maps this to the respective outputs, and then you're applying your softmax loss, for instance, and then you can actually apply a classifier, right? The one thing at the end here, so yeah, this is this final fully connected layer, what I just said. This is the same what we had in the standard MLPs. typically you want to have not that many of these ones. So 1 or 2 fully connected layers is typically the most what people are using. The reason why that is if you're using an architecture like that, depending on the dimensionality here at the end, what might happen is that these fully connected layers at the end might have more parameters than the entirety of your network together. And that's not ideal, that's not necessarily desired, right? Because you want to spend more effort on the feature extraction. So this is something to definitely keep in mind here. Okay, but yeah, common ways like you have basically conv reloop pool, conv reloop pool, conv reloop pool, bunch of times, some combinations of that, and then at the end you have a fully connected layer, and then you have a classifier, and then you're done, right? Okay, now if we are making a comparison of convolutions versus fully connected layers, right? Like these ones are fundamentally different how they're being applied. So in contrast to fully connected layers, we want to restrict the degrees of freedom. We want to add more constraints, meaning we have fewer degrees of freedom and we have more structure how we can apply the filters. And the idea is that these filters are spatially invariant, meaning no matter where you're applying the filter that you apply is always going to be the same. And it's a feature extractor because based on the filter, you're getting a certain activation that tells you, oh, how much was this filter present there? How much was this filter there? That's why we often call it as a feature detector, right? And the idea is that we're exploiting the dimensionality of an image here, right? Like this image domain means that every 2D location here, you can apply the filter and can see, did we detect a feature like this here? Did we detect it here? And detection just is reflected in the activation function, right? So the sliding window with the same filter parameters to extract the image features. We have this concept of weight sharing, and yeah, we have this invariance basically where we're applying the filters, right? And yeah, and as I said before, confnets are the standard for classification, any image operations, downstream tasks, and so on. So one thing we should still talk about is the concept of receptive field. That's important to know when you're designing these networks. So when you're designing these architectures, to be more specific. The receptive field is the spatial extent of the connectivity or convolutional filter. And this is important because you want to have a large receptive field. You want to have, in order to make a decision or to compute a feature, you want to cover as many input pixels as possible such that you're getting a more informed decision, right? That's why you want to have larger filters. But I'll get to this. This has a drawback. There's a bit of a balance you have to do here. But let's first define what receptive field is. Well, receptive field just means, okay, how many pixels are affecting the respective output? Okay, so if I have a 5x5 image and a 3x3 filter, I get a 3x3 output. There's no padding and there's a stride of 1. So what you do here is for this output pixel or for this output location, you had these 3x3 inputs, right? So in this case, well, we have one filter kernel. We are simply getting a 3x3 receptive field, right? Very straightforward because this one output pixel is connected to these 9 or 3x3 input pixels. Now, for one layer, that's very straightforward. Now let's have 2 layers, right? Let's add another layer. We have a 7x7 input. Then we applying a 3x3 kernel here. We're getting a 5x5 input. And then we're applying another 3x3 kernel and we're getting a 3x3 output. So if we are going here, we're having here, this output. And this output has a receptive field in the previous intermediate output of 3x3. That's what we just saw before, right? This pixel or this location is dependent on these 3 input locations. And now I have to go recursively back. And I mean, it's not so complicated to imagine it. Now I'm looking at this one here, at this location. This one was dependent on these 3. Well, 3x3 pixels, right? So this is again dependent on 9 inputs. And now I go to this pixel that's dependent on this one, right? So now this pixel was dependent on all these, and these ones here were dependent on all of these, if I take it all together, right? So my receptive field grows. So it's a 3x3 receptive field, and now I have a 5x5 receptive field, right? This is my 5x5 receptive field on the original input, and the output is connected to to all of these 25 pixels here, right? And you can imagine this grows very rapidly, right? So the more layers you're running, the larger your receptive field goes. And now there's this interesting sweet spot, what I mentioned, right? There's a design decision you have to make. Do you want to have larger filter kernels? Or do you want to have smaller filter kernels that give you a smaller receptive field per layer, but you might be able to have more layers in total? And that's important to consider, right? Like, do we have rather larger or more powerful layers, or just simply have more layers to begin with? And the trend and the tendency for a while was that we wanted to have relatively small filter kernels. So having filter kernels of like 3x3 or 5x5 was very common, even in very deep architectures. You just had a lot of filter kernels and you had a lot of layers. That's how you get a larger receptive field then, basically. And one thing you can also think about it, think about the extreme case where your filter dimension is the same dimension as the input, right? So that's something maybe to consider a little bit more, because the point is, right, if the filter dimension becomes too big, we're losing this spatial invariance. Like what I mentioned is we want to have a smaller filter kernel that applied at many locations and gives us an activation that tells us how relevant was that feature from this filter kernel there. That's what we care about. And I hope this is something you can think a little bit through. In principle, there's not that much math here right now, but there's a very important high-level fundamental understanding of how the convolutions allow us to get localized feature extraction, and then we kind of do feature selection with pooling, and eventually we can design very powerful architectures around it. Okay, with that, we are finished with this lecture. I hope this was fun. I really enjoy always teaching the convolutional lecture because it's a very powerful concept and it's, I think, very easy to visualize. The one thing as a quote-unquote homework, what I would give you is have a look, like just do a bit of the math yourself in terms of figure out the numbers of input dimensions, output dimensions, filter dimensions, strides, and padding. Like that's very important. And whenever you do this, think about how many weights do you have in your current layer, right? How many filters do you have? How many weights do you get as a response? And so on. And I think that would be super cool if you could just try and play around with this, because this helps you really in the high level understanding. So yeah, that's it for today. Again, thanks a lot for tuning in. Thanks a lot for attending. I hope this was also a lot of fun for you. I always like it I always like it actually. With that, thanks a lot and see you everybody next week. See you and bye-bye. Take care.